Are we on? Are we not? Wait, let me check if this works. Oh, perfect. Let me know when we're set. So are we streaming? And this is my voice. Yeah. Oh, perfect. You know, it's a sad, state of affairs when we can actually fold 90% of the chairs. Yeah, that's happening. That's happening. So one of these, ideas I've had is maybe I should not put up the slides on the web anymore. So if you want to see the slides, you have to see the video. Right. That way, and if you want to answer the quiz, you have to see the slides. So put the slides up, 10 days later. Look at the class. There's nobody in class. Okay, you guys, are we set? All right. Morning, everyone. I'm still waiting for the day when the weather gods decide whether it's actually officially spring or still winter. It's kind of miserable. I'm going to need pens. So, can we catch me here at this location? Do we have the other camera? Oh, perfect. Okay. All right. So, wait. So today we're going. So far, we've been looking at networks where we've considered a strictly feed-forward structure. What I mean by that is anytime an input went in, the processing was strictly unidirectional. No unit ever revisited an input, right? So even for recurrent networks, once an input went in, it just kept moving forward. A unit that had processed that particular input would not see that input again. Today we're going to move on for the next 3 lectures to a different class of networks where the neurons actually revisit inputs. And you're familiar with this. The network on top is the standard feed-forward structure we've seen. The kinds of structures we're going to be looking at is something like this at the bottom, where the output of a neuron might actually go back into other neurons, right? Here's a simpler, less ugly, less complicated representation of the same network. So we have in this example 5 neurons. I'm going to assume for the moment that, actually for the rest of this lecture, that the activations of the neurons are threshold functions. So each neuron receives inputs from every other neuron. And if the weighted combination of the inputs from the other neurons exceeds your bias, plus your bias is greater than 0, the neuron is going to output a 1. Otherwise, it's going to output a 0. So every neuron receives input from every other neuron. Every neuron outputs signals to every other neuron, right? Now, this is fundamentally different from everything that we've seen. And specifically, we're going to look at a version of this network where the weights are symmetric. Now, when every neuron talks both ways to every other neuron, then you have connections, weights to connections going from neuron I to neuron J. You also have weights from connections going from neuron J to neuron I. We're going to set both of them to be the same. So these are symmetric networks. In other words, they are undirected. This is what is called a Hopfield network. So how does this not feel? Okay. So if the weighted combination of everything that comes in is positive and the neuron is currently negative, it's going to flip. If the neuron is also positive, it's not. So a neuron flips if the weighted sum of the other neuron's outputs is of an opposite sign from the output sign of the output or current output of the neuron. If both of them match, the neuron will not flip. Otherwise, it's going to flip, right? Now, but what happens if a neuron flips? If a neuron flips, this has a ripple effect on the other neurons. It's going to affect the total input seen by the other neurons, which may now be caused to flip. And if those flip, guess what? Everything's going to come back. Is this a PDF? Okay, good, because there's some animations here, right? So, so if those flip, then that may cause the first neuron to flip, and the whole thing can keep cycling. So here's how we can think about it. At each time, each neuron receives an incoming field, which is a weighted sum of the outputs of all the other neurons except itself, plus a bias. If the sign of the field matches its own sign, the neuron's going to do nothing. If the sign of the field is opposite from its own sign, it's going to flip, right? So I can write it like so. If the product of the output of the neuron and the weighted sum of the outputs of the other neurons is negative, the neuron is going to change its sign, right? Again, these are binary neurons. Output is either 1 or 0. Very simple, right? That explains the logic of what's going on over here. Now we're going to keep seeing that equation again and again, or some version of it. So here's an example. Here you see red and blue edges. So the red edges, I'm assuming that all weights are plus or minus 1. So the red edges are minus 1, the blue edges are plus 1, the yellow nodes are plus 1, the black nodes are minus 1. Now consider this. Let's say I started the network with this particular configuration. So this yellow one is a plus 1, all the others are minus 1. Now consider what happens at this guy. So it's getting a minus 1 from here. It's getting, what is the black times blue? That's going to get 2 minus 1s. And wait, no. So these two are going to cancel themselves. I think I have my signs off. This should have been a plus 1. So in that case, that neuron would flip. So I have some issue with the colors on the edges. But basically what you will see is that depending on the input, the neuron would flip. Now because that neuron flips, some other neuron might flip. And because that neuron flips, this first guy might go back and black, right? And the whole thing can continue. So if the sign of the field at any neuron opposes its own signs, it flips to match the field, which will change the field at other neurons, which may then flip, which may cause other neurons, including the first one, to flip, and so on. So here is a little animation of 20 evolutions of a little network with, I don't know, maybe 20 neurons? I don't remember the exact count, but you saw what happened, right? Or to see, this is very brief. This was just 20 evolutions. But then let's look at something slightly longer. This is 120 evolutions of a loopy network. And you can see what happens. Each neuron, you set the network to some pattern. Each neuron is going to see some incoming field. If the field doesn't match its own sign, it will flip. If it flips, it's going to change the field at other neurons, which might then flip, and so on, yes?
So the state of the system depends on the order of processing of the nodes, right?
Not necessarily. So the actual manner in which it evolves, well, yes and no, right? Yes and no. And I'll tell you why under which conditions it's a no. But in general, the order might change the final outcome. And what do I mean by the final outcome, right? So let's ask this question, right? We just saw that the neurons are going to keep flipping. Will this behavior continue forever? Does anybody want to take a guess? Why?
Because every system can be balanced.
So suppose I give you 2 neurons and the connection between the two is minus 1. Right. Anyway, so the point is, yes, it will not continue forever. And why is that? And I will show you why it is so. So let's consider what happens at a particular neuron, right? The neuron is at some current, has some current output. I'll call that y minus. Then it senses the incoming field, which is this guy, the weighted sum of the outputs of the other neurons plus the bias. And in response to the incoming field, it might or might not change its output, but then there's the the neuron takes a different value after it has sensed the incoming field. So let me call the output of the neuron after it has sensed its incoming field as y plus. So y minus is before it has sensed the incoming field. Y plus is after it has sensed the incoming field. Now, if the output of the neuron is the same as the sign of the incoming field, then y plus equals y minus, right? So if I do if I take the output of the neuron times the incoming field after the change, or after it has sensed the field, minus the same value before it has sensed the field, because these two are the same, it's not going, this value is 0. So this particular value has not changed when the incoming field has matched the sign of the neuron itself. What if it causes it to flip? So if yi minus is not equal to the sign, then yi plus is going to be minus yi minus, meaning the neuron is going to flip. So now let's consider what happens over here. So this term, the same difference, I can group this out as this field times yi plus minus yi minus, but then yi minus is minus of yi plus, right? So this simply comes out to 2 times yi plus times the sign of the field. But then what is this guy? What happened? What did the neuron do in response to the field? It changed its output such that the sign of the field and the output of the sign of the output of the neuron itself changed, right? Matched. The sign of the field and the output of the neuron matched. So this term is always going to be positive, right? So in other words, every flip of a neuron is locally guaranteed to not change or increase the product of the output of the neuron and the field at the neuron, right? So consider that value summed across all neurons for every single neuron in the network. If I consider that, then I can write simply the weighted sum of the products. So for every connection, I can just multiply the weight of the connection by the signs of the neurons on either end and add it across all pairs, and also sum all the bias terms. Now, this is the same definition as the one on top, except that I'm not double counting. I've used I and j less than I, just to make, because I'm assuming that the network is symmetric, right? Now, for any neuron that flips because of its field, it's going to cause a change in this d value, which is this total term, the sum over all neurons of the product of the output of the neuron and the field at the neuron, right? So let's consider the kth neuron. Let's say the kth neuron flipped, or the kth neuron responded to the field, total field. What is the change in d going to be? The change in d is simply going to be, because if I just consider that only the kth neuron, the rest of the terms sort of disappear, right? So all you're left with is this little term, which looks exactly like what we saw for a single neuron in the earlier example, and this term is always positive, right? So every single flip of a unit, if you consider the units one at a time, is going to cause an increase in d. And indeed, if I'm processing the entire collection of neurons, eventually I can just decompose it into the response of individual neurons, right? So every single flip of a neuron is going to result in an increase in d. Now, can this go on forever? It cannot, right? Why? So here's my value of d, which is simply the sum over all the neurons of the output of the neuron times the field at the neuron, and it's bounded because the weights, the y's are all plus or minus 1, right? So in other words, the largest value this can take is simply going to be the sum of the magnitudes of the weights and the sum of the biases, right? Magnitudes of the biases. When I have a bounded value, upper bound on some value, and I give you some function which always increases the value of this d, what can I say about how many steps, how many increments I can actually take when the system evolves? Unless each increment is infinitesimally small, there's going to be a finite number of steps before I hit the ceiling, right? So all I have to show is that each step is not infinitesimally small. Now, what is the smallest value of an increment in d, right? So we saw earlier in the previous slide that this is what the increment in d looks like. It's actually just this guy, right? The magnitude of y is bounded, it's just 1, so I can get rid of y plus this term. I only have to consider what the smallest value for this term is going to be. And so this term, if I take the smallest possible value across all combinations of y, that is the smallest increment that I can have in d when a particular neuron flips, right? So in other words, there's a lower bound on the increment per evolution. There's an upper bound on this d value as the system evolves. So there's an upper bound on how many times these neurons can flip before the system stops evolving, right? So any sequence of flips must converge in a finite number of steps. So if I just take this network where every neuron connects to every other neuron, set all the values to some initial value and just let it evolve, it's going to keep evolving, but eventually it's going to stop evolving. It's going to stop at some point. This is a guarantee, right? Very trivial guarantee. Now this is a Hopfield network, right? So here's how we're going to define this whole process. I'm going to define the energy of this Hopfield network. I just kept calling this value d. We have a name for it. We'll call it the energy of the Hopfield network, which is the negative of d. And we'll see why we use this term energy in a bit. So the evolution of a Hopfield network constantly decreases its energy, monotonically decreases its energy. So I won't say constantly, but monotonically decreases its energy. And yes, I have an update from Windows. Okay. Okay. So where did this energy term come from, right? So we just sort of explained this whole network structure. Where did this energy term come from? How many of you here actually were here for Gerald's talk? Small number. How many saw the video? Nobody, right? So he used a magic word. He mentioned something called an icing model. Anybody familiar with the term? No? Okay. So where did the term energy associated with the, any questions about what we've discussed so far? About the nature of the network, how it evolves, and the overall behavior, and why it must converge, and where this objective function actually came from. We use this objective function to show that there is a property of the network that must converge as the network evolves, and that the convergence must happen in a finite number of steps. And that property is simply this energy term. I'm calling it an energy. There's a lower bound on the energy, and it must arrive at a lower bound, no matter where, which means that the number of steps of evolution is bounded. Now, this energy term actually comes from an analogy in physics. In fact, Hopfield's original network actually was derived, I think, from this analogy, and that's from something called spin glasses. Spin glasses are, the term glass is kind of freely used over here. It's not really, we're not really speaking of glasses. We're speaking of magnetic materials. Magnetic materials are known to have this phase transition where you can go from ferromagnetic to paramagnetic at some point, right? So think of it this way. You have a lot of magnetic dipoles in a medium, and they're disordered. Now, and let's consider only two directional. It's the orientation of the magnetic field is two directional, right? So every dipole is going to try to arrange itself to be aligned with the local field at the dipole. And the local field at the dipole is an effect of two influences: the arrangement of all of the other dipoles in the medium, which are all causing a local field, and any external magnetic field that you might actually impose on the material, right? Now, if the dipole senses a local field which is north-south, and the dipole is currently south-north, it's going to flip to align itself. And if it aligns itself, this has an effect on all the other dipoles. It changes their fields, right? And so when it changes their fields, some of them will flip, and when they flip, it's going to have an effect on the current dipole. The whole process is going to evolve. This is a natural physical phenomenon, and the kinds of materials that are on the kinds of mediums on which this property can be observed are sometimes called spin glasses. So here's how you can think about it. there's a total field at the current dipole, I, which is the sum over all of the other dipoles times the, field from the dipole, and Ji is how much a dipole that's not at the current location influences the current location. It's going to be dependent on many different things, including how far away the other dipole is, what other, it's not going to be a pure medium, what else happens in between, the geometric arrangement, the dipole electric of the medium, etc. But this is going to be specific to the other dipole, right? So you have every other dipole is going to influence the field at the current location, and then you have an external magnetic field. And so all of these together create a total magnetic field at the current location of the current dipole. The field at any dipole is the sum of the field contributions of all the other dipoles, and the contribution of a dipole to the field at any point depends on the interaction J. So this model was originally proposed by a guy called Lenz in 1920, and this was worked out by a fellow called Ising in 1924 in one dimension as part of his PhD thesis. And he came up with the conclusion that in one dimensions, it was kind of uninteresting. He wrote a paper about it. Then, he found the whole thing so boring, he gave up physics and went away and became a school teacher. This was 1924. 25 years later, he randomly opened a physics book, and he found that he was being cited all over the place. So, that's the kind of, anyway, 1949. Amazing, huh? So here's the overall model. So we call it the Ising model after the guy. And the Ising model is more, the spin glasses are a specific instance where the Ising model applies. So the total field of the current dipole has has the value on top. The response of the current dipole is that it's going to remain the same if the field doesn't tell it to flip. Otherwise, it's going to flip if the field does tell it to flip. This is physics, right? So dipoles will keep flipping. A flipped dipole changes the field at other dipoles, some of which will flip, which will change the field of the current dipole, which may flip, and so on. Looks just like your Hopfield model, does it not? And specifically, when will this stop? You can define, again, this is a term that you might have heard Gerald pull up, Hamiltonian. You can define a Hamiltonian of the system. The Hamiltonian is nothing but the total energy of the system. It has two components, which is the, what is the potential energy of at any dipole? It's going to be the value of the dipole times the field of the dipole. If you've gone through your first class in physics, you're familiar with this formula, right? Plus whatever energy it has due to the external field. And what happens to a system when you set it at any particular energy? It's going to keep losing energy till it comes to some configuration, right? To some steady state configuration, and the steady state configuration is going to depend on the temperature, the external field, etc. So this Hamiltonian measures the total energy of the system, and the system is going to evolve to keep reducing its energy until it cannot reduce the energy anymore. And again, so here's how you'd have, this is the kind of behavior you'd expect to see. You have a state for the system. I'm drawing it as a continuum. Clearly, it's not a continuum. It's a discrete thing, right? You have a bunch of dipoles, and depending on how many dipoles you have, the number of possible states is going to be 2 raised to n. If you have n dipoles, I'm just drawing it as a continuum. For each state, each configuration, you have a total energy, Hamiltonian, and you can plot it. And if you set the system at any particular value, the system is going to evolve till it hits the valley, at which point it can't go down anymore. You might have multiple valleys, but it's going to evolve till it hits the valley. And this is the standard evolution of the system. And if the system is in some stable configuration, if you jitter the system, flip a few dipoles, what will happen? It's going to start evolving again till it goes back to exactly the same steady state, right? To the stable state. So, in other words, the system remembers the stable state. One way to think about it is that the system remembers the stable state. And if you jitter it from the stable state, it's going to come back to the stable state. Now, this has a very nice analogy, according to Hopfield, to human memory. And we'll see how, right? So a Hopfield network looks just like that, does it not? You have exactly the same properties. If you thought of each of these neurons as a dipole, it has an influence on every other neuron. You have a total field. and those things are going to try to align themselves to the total field. You can define the energy of the entire network, very analogously to the Hamiltonian of the spin glass, and the system is going to evolve until the energy hits a local minimum. So now when I wrote it this way, I included this bias term, which in the physics world would be the external magnetic field, right? So typically when we design computational equivalents of Hopfield nets, we won't explicitly use biases. If you don't, so I won't, in some of my equations, I actually won't have the biases. Removing the bias doesn't affect the overall interpretation of the network, but we're not going to kill the bias. It'll come back into the discussion, right? Anyway, so here's what how you'd expect the network to behave. You'd have some initial state, and then it's going to have some energy. And if if I let the system loose, it's going to keep evolving. The state is going to keep evolving till it hits some configuration where any further evolution is not going to decrease the energy of the system, at which point it will stop evolving, right? So the network will evolve until it arrives at a local minimum in the energy contour. This is what we will call a content-addressable memory. So have any of you heard this term? CAMs, content-addressable memories. So what is your standard format for memory when you store memories in your network, in your computer? They're addressed by an external address location, addressed based on location, right? In this grid of memory locations, every location has a specific address. If you want to invoke whatever, that particular element, you're going to have to pull up the location and say, give me the memory whatever is stored at this specific location. So they're location addressable. But the flip side is something called content addressable memories, where you kind of partially remember patterns, but then when you start off from the partially remembered patterns, you eventually invoke the entire memory. Now, human memory works in some, in that same manner to some extent. If you just start off, something invokes it, you're walking somewhere, you smell something, which invokes some pattern, and then you suddenly remember things that happened long ago. But more generally, if you think about how you actually recall things, it starts off with a partial memory, which just sort of evolves into a complete recall of whatever it is that you're trying to consciously or unconsciously recall, right? So it's content addressable. This Hopfield network is a content addressable memory. So if I think of these locations as the patterns that the network stores, then if I set the network to some pattern which is somewhat close to it, it's going to evolve till it arrives at the stored pattern. So I give it a corrupted version of the content, it's going to come down and give you the actual value. So it's content addressable memory. It's also called associative memory. So here's how it would work. You define the energy of the network. The energy is going to have some contour like this, and we'll see in the next class why all these figures are bogus. They're rubbish. But anyway, the energy is going to have some contour like this. If I start the system at some point, it's going to begin evolving till it arrives at the closest energy minimum, local minimum, and then it's going to stop there. So you might think of this as, partial content that you've set the network to, and the system evolves till it recalls the entire content. So it's content addressable. Now, and since we proved that every change in the network is guaranteed to result in a decrease in the energy of the network, the path from wherever you are to wherever you're going to is going to be monotonic. This is to answer the question of the order of computation, right? Now, the path is monotonic. It doesn't mean the path is the same, right? I could actually be going down like this. I could be going down like this, depending on the order in which you process it, but you're going to end up at the same point, right? Okay. Now, I've used threshold activations in my function network. You don't need threshold activations. You could use other activations. If I use threshold activations and I define the output of my network as being, of my units as being strictly +1 or -1, then it's the equivalent of saying that I have a hypercube in n dimensions, and every point is every possible configuration of the network is one corner of this hypercube. Some small subset of these corners are these memories that the system will recall if I start off somewhere in the vicinity of these memories and let the system evolve. Questions? Anyone? On the streaming, any questions? None? Okay. So instead of these threshold activations, if I use tan H activations, you're going to get not just functions defined at the corners of the cube, it's going to be more continuous through the whole thing, right? So I now also mathematically, if I want to write the this energy term on top, I can write this in matrix form like so. It is minus half y transpose wy, where w is the weights matrix. So it's the inner product, weighted inner product between the of the weighted norm of the state vector, and why the minus half over here if you compare it to the equation right here. So because I'm using everything just once, so if you look at the summation, you're saying, going left to right, you're not double counting j less than I. So to account for it, I need a minus half, right? And what are the diagonal elements of this weight matrix going to be? They're all going to be zeros because no unit connects to itself, right? Okay. So here is an example of the kind of the energy contour that you might see. This is an example where I have only two neurons. The two neurons are connected to themselves by weights W1, 2, some way, right? So this is the input. The scales seem to be somewhat off. But then as the outputs of the neurons change, the overall energy of the system is going to change, right? And you see that there's a unique minimum where the energy is a minimum. But it's not unique. There are two minima. So the structure seems to have two bowls, right? Why are there two minima? Ignore the axes for now, right? Why would you expect to see two minima? Go back and look at this equation. If I have y transpose wy, if I replace y by minus y, does the energy change? Because the two minuses will cancel out, right? So if for any pattern that's a memory, if I flip the sign of every single bit in the pattern, that too is going to be a memory, right? So that's why it has two minimum in this case, okay? Symmetric because minus half y transpose wy is the same as minus half minus y transpose w minus y. So if y hat is a local minimum, so is minus y hat, okay? There's some bogosities in the figures because some of them are pilfered and maybe out of context when they are. I'll let you know, okay? Now here's a little 3-neuron network. This has 8 possible states because each of them can be minus 1 or plus 1. And there are only 2 stable states. What do I mean by 2 stable states? These are the 2 local minima. So that's the one neuron over here, one state over here, and the other state over here. And if I start anywhere, it's going to end up at one of these 2 stable states. And now this is here is an example of content-addressable memory. So how exactly does it work, right? I can set this guy. I have trained a Hopfield network. That's a picture. Every pixel is plus 1 or minus 1. And I've trained a Hopfield network such that this pattern is the pattern at which the network has the minimum energy. Now if I initialize the network with this guy, which is pretty crappy, the system is going to evolve and it ends up over here. It's basically recall the pattern, right? Yes. No, you can go ahead. Similarly, here's another example. This thing is for the Chippendale, right? So it's been initialized with that little picture. It has been designed, trained, such that this Chippendale pattern is the memory that it's going to recall. And then if you initialize the network using this half the picture, it kind of evolves, and the animation isn't exactly what it's supposed to be, but it evolves and gives you this guy, right? So you can see how the whole thing works. I think, can you play the video here? So it's trying to, this is another example I got from YouTube where they're trying to store different patterns. And then when they initialize it with different patterns, right, very noisy stuff, you see how it actually falls into, ends up recalling one of these guys, right? And they're actually rubbing things out. It's pretty cool, right? Now you'll observe that he's actually managed to store multiple patterns, right? Why would you expect that to happen? Why would you expect the network to have multiple memories that it could recall? The energy contour has multiple local minima, right? So you would expect it to have multiple values that it could recall. So the computational algorithm, assuming that you have this, yes?
Can you go back a couple slides on Loopy?
Yeah.
So is there any intuitive explanation why for the bunny one there's like all these like sort of little patches of white and the reconstruction?
Yes, we will get to that, right? And it's a huge problem. I mean, it's not, when I have almost trivialized the explanation that I've given, because reality is much more complex, as you will see in a few slides. So here's the, assuming that the network has been trained, here is the overall pattern behavior that you'd expect, algorithm you'd have. You'd initialize the network with some initial pattern, and then until convergence, you're going to sort of cycle through each of the neurons, check the incoming field. If the incoming field says the neuron must flip, it will be flipped. Otherwise, it won't be, and then you keep continuing till the whole thing stops changing, right? And updates can be done sequentially, one at a time, or all at once, meaning you take the current state of the network, test every neuron, decide if every neuron will be updated, and repeat the process. All of them are eventually going to end up at the same position regardless of, or you'd expect everything to end up at the same position regardless of how you do it. Now, yes?
How do we know how many local minima a given network may have? So like what's its capacity to remember?
Yours. Okay. So I just gave you some examples where it remembered some patterns. How did we make it remember those patterns? And how many patterns can we actually remember? This is to answer your question in some great detail, right? And there's a third question that we can actually ask. Can I do something to make up this whole business of retrieving the correct memories even better? And this relates to the other question, what were those little white dots doing, right? First, how do we make the network store a specific pattern or a specific set of patterns? We're not going to get much beyond this in today's class because, so how do I teach the network to remember, say, this little image from Looney Tunes, right, or Chip and Dale, right? Now this is, for an image with n pixels, obviously we're going to need a network with n neurons. Every pixel is one neuron because you're storing the bits, right? It's content addressable. And every neuron is going to connect to every other neurons. We are assuming that the weights are symmetric. So how many weights will we require? N squared over 2, right? Or n times n minus 1 over 2. Again, you could cancel off the fact that you don't need the diagonal terms, and so it'll be a few fewer, right? Now, this is, so now we must keep in mind that any network that stores a pattern also stores its bit reverse. So in other words, in this example, if you stored this guy, you'd also be automatically storing the exact inverse, where all the blacks are white and whites are black. And from our perspective, they are both the same thing. We shouldn't care. Okay. Now, and that means that that's because that means the energy at p is going to be the same as the energy at minus p, and this is how we've defined the energy, if you'll recall. Now, a network can store multiple patterns if the energy contour has multiple minima, right? Every stable point is going to be a stored pattern, so we could design the net to store multiple patterns. And remember that every stored pattern is actually two stored patterns, p and minus p. Now, before I even continue, right, those of you who are mathematically oriented should be screaming at me. Because, why? Let me go back a few slides. And I'm going to say, I'm going back many, many, many slides. Look at this equation over here, and I've just told you that it has multiple local minima, right? So why are you not screaming at me? What kind of a function is it? Yes, it is convex. It's more than convex, right? What kind of a function is it? Do you mind shutting your laptop? You back there? Can you shut the laptop? Yeah. So what kind of a function is this? It's quadratic, right? How many minima will a quadratic have? 1. So what do I mean by saying I have multiple local minima and drawing all of these beautiful plots with multiple local minima? Obviously it does. The entire field hasn't been lying to you, right? So, but then math tells you it shouldn't be the case. Something is off. Can anybody take a guess as to what is off? You know the answer. So it's a quadratic. There's only one. There is no multiple local minima. There are no multiple local minima, right? And anyone? Okay, we'll get to that in the next class. But suspense, right? But here, so here's our task. We want to design the weights matrix W such that this energy has local minima at the desired patterns that we want to store. Now consider the case where I have only one pattern that I want to store. I want to store the Looney Tunes picture. That's it. I don't want to store anything else. So now in this case, I want to design the Wij such that the energy is minimum for the Looney Tunes picture. So we want, what does it mean for that pattern to be a local minimum? You want the sign of the weighted combination of the outputs of all the other neurons to be the same as the sign of the neuron, target sign of the neuron itself for every single neuron. This is the objective we need, right? If this is satisfied, no bit is going to flip. That's a stable pattern, correct? So this is a stationary pattern. There's a difference between stationarity and stability, and we'll get to that as well. So we're going to use Hebbian learning. Anybody remember what Hebbian learning was? Way back when. So what was Hebbian learning? We just sort of, we just took the product of the input and the output, and we incremented the weights by the product, some scaled version of the product of the input and the output, because we are saying that for every input, the output must be aligned with the input. This was the basic Hebbian learning rule, remember? So in our case, Hebbian learning is going to be that the weight that connects neurons I and J is simply going to be the product of neurons I and J. And now this makes sense, right? So if I and J are different signs, then basically you want the weight to be negative. So because if Yi is minus 1 and the weight at W is minus 1, then Yj is going to see minus 1 and times minus 1, which is a plus 1, so Yj will not flip, and vice versa. Whereas if the Yi and Yj are the same sign and the weight were negative, then it's going to be causing them to flip, right? So it makes sense that each weight must simply be the product of the two neurons that it's connecting, right? So this is the basic Hebbian learning. So here it is. Now let's see if this Hebbian learning actually works. So this is very trivial. I'm trying to store one pattern. I took a very simple rule. I'm going to connect every neuron to every neuron. And the way I set the weight of the neuron is that I'm simply going to set the weight to be the product of the two bits that I want to store within the target pattern, right? So will this really work? Let's check if this works. Now, you basically consider this, that what is the total field at any incoming neuron, at any neuron? The total field is going to be the weight of the outputs of all the other neurons. Sign has to match the sign of the current bit itself. But the weight that we set it was simply wji was simply yj times yi, right? So I can say yj times yi times yj. But what is yj times yj? Yj squared. This is the sum over all j not equal to I, yj squared times yi, right? And what is yj squared? It's always 1, right? And of course, yi is not something that I'm summing over, so this comes out. So this is a positive constant. This is going to be some positive constant times yi. What's its sign? The same as yi, right? So this is going to be the sign of yi, which is yi. So if I use the simple Hebbian rule, you're guaranteed that the current, the pattern is stationary. What do I mean by stationary? If I set the network to that pattern, it's not going to begin evolving, right? Now, here's another thing. The pattern is stationary. Now, let's check something else. What will the energy be, total energy be, if I actually set it to be the Hebbian? So we use the Hebbian rule to learn the network. That's going to be the sum over all pairs of neurons of the product of the bit values times the weight. But if I use the Hebbian learning rule, wji is simply going to be yj yi, correct? So this is going to be yi squared, yj squared. This is simply going to be, all of these are the 1. These are 1, right? Now, within this setting, what is the smallest value that the energy can possibly take? The smallest possible value that the energy can possibly take is that if every argument is 1, correct? And that's exactly what we are getting. So in other words, this is the global minimum of the energy as well. So in other words, this pattern is stable. What do I mean by stable? If I flip a bit, it's going to come back. If I flip 4 bits, it's going to come back, right? So these patterns are stable. So we've shown that the Hebbian learning rule actually gives you a network which stores the pattern that you want to store for one pattern. And let's try to visualize this. So here's a little 4-bit pattern. So I have 2 of the bits shown on the x-axis, 2 of the bits shown on the y-axis. The pattern that I'm trying to store is this guy, which is 1 minus 1, 1, 1. Okay? And now if I use the Hebbian learning rule to actually learn the weights and then compute the energy for each bit pattern, right? So how many bit patterns do we have? We have 16-bit patterns, and I've drawn them as a map. Remember the Carnot map from lecture 2, right? So this connects to that edge, this bottom connects to the top, so the whole thing's a toroid. I've drawn this as a map, and I'm plotting the energy for every single bit pattern on this map, and this is what the energy contour looks like. And observe that it has a minimum at the pattern that we want. It also has a minimum at the flip, right, where every side, which is what I'll call its ghost. And also observe the gradation of these energies, right? No matter where I begin, if I start at this point, it's either going to travel this way or this way. So this is to go back to the other answers. It's not going to necessarily, if you're on the ridge, you could go either way depending on the order in which you begin processing things, right? And then once it goes here, there's only one way for it to go. It can't go here, it cannot go here because the energy must keep decreasing, so it comes here. So now this is stable, right? Regardless of where I begin, I'm actually going to end up at the pattern that I'm trying to store. So this works, right? Now if I'm trying to store multiple patterns, more than one pattern, can I use the same logic? So I can still use Hebbian learning. And if I'm using Hebbian learning, what I will do now is that I'm still going to use the same rule, except that I'm going to sum over all of the patterns that I'm trying to store, right? Very simple. So I have a set of patterns that I'm trying to store, and for each pattern, I take the product of the 2 pixels, which I'm connecting using this weight, and sum over all of the patterns. I could average it too. It doesn't really matter. The constants don't matter. We're only worried about signs. And that's going to be my weight, okay? So if I use this kind of storing pattern, now we've shown that we can definitely store one pattern. It's stable, it's stationary, one pattern can definitely be stored. How many patterns can I store, right? Now, John Hopfield came up with this arithmetic which said you can store up to 50, if you have n bits, you can store up to 0.15 n patterns, right? Now, keep in mind that there's a difference between storing patterns and having stationary patterns. In other words, when I store patterns, these are intended patterns. These are the patterns I want to store. But in the process of storing those patterns, I may end up with a network which also remembers other spurious bogus patterns. which I don't want remembered at all. So these are what we will call parasitic memories, right? But then target patterns, John Hopfield claimed that you can actually get stored up to 0.15 n patterns, provided they are far enough. Where did this number 0.15 come from? Now, take a look at the following. So let's say I want to store k n-bit patterns of this form. So this is just the indicator. This is just the representation yk is the kth pattern. But then when I represent it explicitly as a bit string, I move the k to the superscript just because I need space to mark everything. And the subscript represents the bit index. So it's yk1 through ykn. There are n bits in the pattern, and then there are uppercase k such patterns that I want to store, right? And let's say I'm going to use Hebbian learning. And remember, I mentioned that Hebbian learning, you can scale the weights. It doesn't really matter, right? It's just all you're worried about is about the sign. So I'm going to scale the weights just for mathematical convenience. So each weight is going to be the sum over all patterns of the product of the 2 pixels, and I'm normalizing it by the length of the pattern, 1 over n. The 1 over n is irrelevant for the actual operation of the network, okay? So now for any network, for any, what? So this is not a minus, this is a 1 over n is the factor, okay? So for any pattern yp to be stable, this, holy, I should not have a, this is correct. There's no 1 over n here. So this guy has to hold, right? The product of the field at each neuron times the value of the neuron itself must be greater than 0. Otherwise it will flip. So for the pattern to be stable, this must hold. And then plugging in the value for wij from here, I get this behavior. The value of that for each pattern, for each pixel, for each bit, the value of the bit times this guy, right, which is 1 over n times the sum of the bits, products of the bits for overall patterns, times the corresponding jth bit for that pattern. This must be positive, right? The actual arithmetic is not relevant. I'm just going to, that it sort of comes in, it's useful for the analysis. Now, observe over here that when I computed the weight, I actually computed the weight through Hebbian learning by summing over all the patterns I'm trying to store. Let me separate that into 2 components. So if I'm trying to analyze the stability of the pth pattern, right? So let me separate out the contribution of the pth pattern and everything else. So this guy here is the contribution of the pth pattern. I'm summing over. So if I set the network to the pth pattern, right? What is the contribution of the pth pattern when I was learning the weights to the overall energy? And this other guy is the contribution of all of the other patterns to the energy term. So again, the details of the arithmetic are not so relevant, except that here I'm going to be multiplying yip, which is the current bit whose stability I'm testing, by the field, which is weights times the bit value at each of the other positions summed over all positions, and the weight I separated out into the contribution of the pth pattern and the rest of it. Now look at the first guy, right? In the first guy, I have yjp. Those 2 are going to become, the product of the 2 is always 1, right? Similarly, I have yip and yip. The product of the 2 is always 1. So this entire term is simply 1 over n times n. So the first term is simply going to be 1. Because this term that I'm summing simply becomes 1, right? I'm summing n of those terms, so the sum becomes n. I divide by n, those 2 go away, it becomes 1, right? So the only thing that I have to be worried about is the second term. So in other words, for the ith bit to be stable, I want the second term to be greater than -1. If the second term is less than -1, if the second term is less than -1, then this term is going to turn negative, right? And the bit is going to flip, right? So what is the probability? So in other words, so I want this to be greater than -1 for stability, or if I want it to be unstable, I want this to be less than -1. This is the contribution. This is the criterion that I have for the pattern to be unstable. Now, the purpose of writing all of this little arithmetic out is simply to show that all I'm really testing is the value of the sum of a certain number of binomial variables to see if that sum is actually less than -1, right? And this can be easily enough tested. It's a sum of a bunch of variables. All of them take value plus or minus 1 with probability 0.5. And if you work out the arithmetic, so let me just write this whole thing as some term C. If you just write out the arithmetic, it turns out that for a large enough n, and for trying to store a large enough number of patterns, the whole thing can be approximated by a Gaussian with 0 mean and whose variance is k over n, where k is the number of patterns you're trying to store, and n is the number of bits in the pattern. And so you really want to say, what is for a Gaussian random variable, what is the, if I randomly drew something from the Gaussian random variable, what is the probability that that guy is less than -1? And if you work through the arithmetic, it tells you that that if you want the probability that if I randomly choose a collection of k patterns and try to store them, and if you want to guarantee that the probability that any one of them is going to be any single bit is going to be unstable, to be less than 0.004, just an arbitrarily chosen number, then you want k over n to be less than 0.14. So this is where Hopfield's equation came from, where he said that a network of n neurons trained by Hebbian learning can store up to 0.14 n patterns with low probability of error, which means that the probability that any single bit will flip is going to be less than 4/10, right, of a percent, so 0.004. All of this is computed using the probabilities of the bits are 0.5. So this entire analysis is computed assuming that the patterns that you are trying to store are very far apart. Meaning, if I take any two patterns, within any pattern, the probability of any one bit being +1 is 0.5, and the probability of it by the bit being -1 is 0.5, right? So these patterns are very far apart. In that case, using Hebbian learning, you can store up to 0.14 n patterns. What is the behavior you'd expect if the probabilities of the bits were less than, if the patterns were less far apart? That is, if the probability of any bit taking the value 1 was less than 0.5. In that case, the target patterns are closer, right? Because they're not perfectly random. So what would you expect the behavior of a network that's trained with Hebbian learning to be in those patterns? Would you expect to be able to store more patterns or fewer? Fewer patterns, because they are closer and you expect it to be more confusable, right? So let's see if that really is what happens. Here is the example again where I'm trying to store only one pattern, simple Hebbian learning, right? And no big deal, it's exactly the same picture we saw. But so that see that for every pattern we see a shadow pattern, right? Which is the flip when you flip all the signs. Now consider this business of trying to store multiple patterns. I will say two patterns are orthogonal if the two of them, if I will say two n-bit patterns are orthogonal if the two of them differ in at most n minus, in exactly n over 2 bits. That's the largest distance between two patterns, right? For us, a pattern is the same as the minus of the pattern. So if I give you two patterns, what's the largest distance between two patterns? It's going to be n over 2, which means half of them match, the other half don't match randomly, right? For every bit, you're basically flipping a coin to decide if the two patterns match or not. So if you actually think of if you compute the inner product between these two patterns, you're going to find that the inner product is 0. So the patterns are orthogonal. So two patterns that differ in n over bits are going to be called orthogonal. And for any n, which can be written as 2 raised to m times l, where l is an odd number, you can show that there are at most 2 raised to m orthogonal binary patterns. We won't work through the arithmetic, but pretty much any number on Earth can be written in this manner, right? Where L could be 1 and M could be 0. So any number on Earth can be written in this manner, and that's how many binary patterns you're going to be able to, orthogonal patterns you're going to be able to find. So now let me try to store two 4-bit orthogonal patterns. The two patterns are 1, 1, minus 1, minus 1. This is 1, 1, 1, 1, and you can check that the two are orthogonal, meaning if I multiply the two, component-wise and sum them up, the sum is 0, right? And now I'm plotting the energy contour, meaning what is the energy of the network for different configurations of 4 bits. And you can see, sure enough, that these 4 guys have the lowest energy, right? but the patterns are perfectly confusable for recall. They're as far apart as possible. On the other hand, if I start at any point, there's no saying which pattern I'll end up recalling, right? If I flip the first bit, I'm going to end up here. If I flip the second bit, I'm going to end up here. So as the probability of recalling the correct pattern from any initial location is just 0.5. So although the patterns are nice and stationary, as far as recall is concerned, if you're more than 1 bit away, even if you're even only 1 bit away, observe this. If this is the pattern I'm trying to remember, if I'm out here, I could flip around and go to that guy, which is the ghost of this fellow, right? So even if only 1 bit has changed from your pattern, your ability to recall anything is perfectly random. So while you're able to say whether something is a valid memory, you cannot recall anything. And these are two orthogonal patterns I'm trying to remember, as far apart as possible. Let me take two non-orthogonal patterns. So these two patterns are no longer orthogonal. This is 1 minus 1 minus 1 minus 1, and this is 1, 1, 1, 1. So if you just compute the inner product between the two, you'll find that it's not 0. In this case, here is the energy contour. Something surprising, right? You're not only able to remember both patterns, they're perfectly, you can recall them. If you start from here, you're going to end up here, right? If you start from here, you're going to end up here. So you actually are able to recall the patterns, although they were actually closer than the orthogonal case. So, it's kind of counterintuitive, right? If you try storing patterns which are really far apart, you are less able to recall these things than when they are less far apart. But then there's something else that comes in. What is 0.14 times n over here? So n was 4, 0.14 times n is less than 1. Using Hopfield's formula, you would say that you cannot store even one pattern using 4 bits. I've shown you an example where I can actually store 2 patterns, and they're recallable, right? So all patterns are local minima. They're stationary and stable, but recall from perturbed patterns, something funny is going to happen. I don't know what the text there says. So can we get rid of this text in the corner? Pick a time. Say pick a time. I don't want it to. Okay. No, this text is kind of bogus. So here, when I try to store 3 orthogonal 4-bit patterns, again, all 3 are local minima, as you will find, but again, you cannot really recall any of these 3, right? And whereas if I use non-orthogonal 4-bit patterns, again, all 3 are local minima, but some of the patterns can be recalled. In fact, in this case, all of the patterns can be recalled, in the sense that if you start close to the pattern, the natural evolution of the system is going to go into the pattern. If I try to store 4 orthogonal 4-bit patterns, all of the patterns are stationary, but guess what? Any pattern is stationary. It doesn't matter what the initial value of the network to be, it's not going to change. So you don't remember anything. And if they are not orthogonal, then there's at least one stable pattern that you can recall, although the rest cannot be recalled, right? So now Hopfield said that for a network of n neurons, you can store up to 0.14 n patterns. And this is a fuzzy statement, because clearly I've shown you that his analysis was assuming that the patterns were as far apart as possible. The probability of any bit was 0.5. Whereas if I gave you non-orthogonal patterns, you're actually able to store more in many cases, right? And so his worst case analysis doesn't quite give us the behavior that we actually see. And it's a fuzzy statement. What does he mean to say store 0.14 n patterns? Does he mean stationary? Does he mean stable? And in any case, n equals 4 is probably not a good example, because 0.14 times n is less than 1 pattern, right? So let's try something a little more complex. This is a 6-bit pattern. Now here, this is a crazy kind of map. So to think about what this map really is, you should fold it down the middle on itself, fold it down the middle vertically on itself, and then roll the whole thing and make it a toroid. It's like a 4-dimensional toroid. To actually visualize neighborhood over here, I just sort of opened it up so that you can see what happens. And now if I try to store only one pattern, you see that it's clearly the pattern and its ghost are very clear local minima, right? But if I try to store 2 orthogonal 6-bit patterns, both of them are perfectly stationary, perfectly stable, but then you see several spurious minima, which goes back to your question, where did the dots come from? So suppose I started over here, this guy. This location is perfectly stable, and if I were to start here, this is going to go into this location and not evolve any further, right? So that's a fake memory, something that I'm remembering, which is not something that I really want to remember. I have to be close enough to the actual memories to remember to recall those yellow spots. But there are other spots in the map which can end up being recalled, which are not things that I really want to recall, right? Now this is again a 3D K-map, right? If I try to store two non-orthogonal patterns, it turns out that the number of fake memories are actually fewer. Things get disorganized a little bit, but you can still quite nicely recall both patterns. If I try to recall 3 non-orthogonal 6-bit patterns, observe that when I have 6 patterns, I cannot have more than 2 orthogonal patterns, because 6 is 2 times 3. 3 is an odd number. The largest number of orthogonal patterns I can have is 2, as I explained earlier, right? So if I try to have 3 non-orthogonal patterns, I can still find 3 perfectly stationary patterns, and many of them can be recalled. They're stationary and stable, right? And in fact, this is crazy. When I try to store 3 non-orthogonal patterns, I end up with fewer fake memories than when I try to store 2 orthogonal patterns. So, if I try to store 2 patterns which are very far apart, and instead I get more fake memories than if I try to store 3 patterns which are not that far apart, which is kind of crazy, right? So, these kinds of behaviors are sort of thought of as being somewhat analogous to how we remember things. If everything you remember is very far away from everything else you remember, then you have lots of room to create bogus memories. If things are close enough, there isn't that much room to create bogus memories anyway. Okay, so this is with 4. And again, in the case of 4, you get some interesting patterns. I can keep going on, right? By the time I get to 6 non-orthogonal patterns, nothing can be remembered. The whole thing kind of breaks down, because what happens is that the reflection of each pattern, the negative, ends up being too close to some other pattern, and they interfere with one another, which is one of the things that happens. Now, I can go on and take 8-bit patterns. This is like a 4-dimensional tesseract. I can store 1 pattern. I can store 2 patterns in 8 bits, but you can see all of these nice fake memory structures, right? I have, this is with 3, I think. With 2 non-orthogonal patterns, you don't actually get any fake memories in the 8-bit case. I can store 4 orthogonal patterns. I can store 4 non-orthogonal patterns. You get the idea, right? By the time I get to 8 patterns, the whole thing is wiped out. So the question is this. This is neither stationary nor stable. So what we have is that we have many parasitic patterns, undesired patterns that also become stable or attractors. What I mean by attractors is that if you start off close to the pattern, it's going to end up in that pattern, right? But we also observe that apparently there's a capacity to store more than 0.14 n patterns, right? As you can see, in the sense that I was able to store with 8 bits, I was easily able to store 3 and even 4 patterns. That's 0.5 n, right? So let's consider this business of parasitic patterns. Why do I get all of these fake patterns which do end up being remembered? There are 2 reasons for this. The first is this. If you work out the arithmetic, if I try to store patterns YA, YB, and YC, right, then the sum of these 3 patterns also ends up being a local minimum in the entire energy contour. So the sum of an odd number of target patterns also ends up being a local minimum in the energy contour. So here, for example, if I try to store these 2 patterns, I'm going to get a small little dip in the energy somewhere exactly. I mean, these are just 2. In theory, it's going to be the sum of all 3. So if I look at the sum of all 3, I'm going to get a dip. The more patterns I add, I'm going to get various combinations of odd numbers of patterns, and those are highly likely to be local minima, right? And then, of course, there's a purely random behavior. You're just going to have random local minima if you have, if you design your network in this way. Now, this is only true if you're using Hebbian learning. Everything that I've been saying so far assumes that you're using Hopfield's original proposal for Hebbian learning, right? So now let's look at the second thing, capacity. How many patterns can I actually store? It seems that I can store more than 0.14 n patterns, right? So in other words, I should be able to obtain a weights matrix that stores more than 0.14 n patterns. But then I don't get the nice, but you know, I don't have guarantees. The probabilistic guarantees that we saw earlier are based on the Hebbian learning rule, because you just plugged in the Hebbian formula for the weights when you were computing the energy and computed your patterns, right? Also, we find that patterns that are non-orthogonal are easier to remember, meaning patterns that are closer seem to be easier to recall than patterns that are farther apart. So there seems to be a certain degree of inability to predict exactly what is remembered and what is going to be remembered well, what are the fake pattern memories going to be, whether the target memories are going to be remembered at all, or how well they will be remembered. This lack of control is because we don't really have a nice controlled way of designing the weight matrix. We just take any odd set of patterns, you compute use the Hebbian rule to learn the weights, and you say, this is it, this is my network. And whatever behavior you get from it is what you get. So the question is, if I change the learning rule and say, go to something that's non-Hebbian, can I actually do better? Can I get better capacity and have fewer spurious memories? And here's the bold claim. I can always store up to n orthogonal or orthogonal patterns with perfect stationarity. Why? We'll get to that. I can also store n arbitrary patterns, so long as they are linearly independent. Any set of n linearly independent patterns, provided such that they are stationary and stable. Not only that, I can avoid spurious memories by adding some noise during recall, right? So you saw those little dips we saw in the energy contour. During recall, if I add a little bit of noise, which allows the system to evolve, even if I'm in a local minimum, then it could escape the small dips and go into the larger dips, right? And go into real memories as opposed to fake memories. So these are the two claims, and these are the claims I'm not actually going to back up today. For this, I'm going to sort of hold you in suspense till the next class. We'll stop here. But even before I continue, there are a couple of, just a bit of look ahead, right? A, have you thought about why the quadratic business doesn't work? Because y's are discrete. So what really happens is, when I define a quadratic, I'm defining a quadratic in continuous space. But the values that the y's can take are on the corners of a grid, correct? So on the corners of the grid, I can have any pattern at all. Whereas in continuous space, there's only one global minimum. And we'll see an why this is so, number one, right? Number two, why would I always be able to store n orthogonal patterns? Exactly, right? If you give me a set of n orthogonal patterns, I can always compute a matrix W for which they are the bases. And if I just set my weights to be that matrix, they become stable, right? So, which basically means that everything that we've seen so far is kind of not quite optimal. And then, of course, you can optimize things on top of that. We won't get to that, right? Now, the third question is, can I store more than n patterns? Clearly not by design. You might get more than n memories, but all but n are going to be fake, right? Clearly not by design. But I'm going to claim that yes, I can store more than n patterns. How would I do that? This is when you think outside the box, right? You become Sejnowski or Hinton. Yeah.
Find all patterns that you want to store.
That's one. Well, that's cheating, right? So this, then you say if I'm going to be storing, there's a relationship we had over here. If I'm trying to store n-bit patterns, what was the size of my network? N neurons, right? N times n minus 1 over 2 weights. Who said the neuron network must have only n neurons? So if I want to store more than n patterns, why don't I just append a bunch of don't care neurons? Right? If I append a bunch of don't care neurons, then the capacity of the network scales with the bit, the number of bits, correct? So which means the capacity of the network is going to be, if I add another k neurons to my n neurons, the capacity is going to be n plus k. I can just keep adding more and more neurons and store more and more patterns, right? That gives us a Boltzmann machine. So just take your standard Hopfield network, append a bunch of stuff you don't care about, you end up with a Boltzmann machine. And in fact, if you separate those two guys in the manner in which the two sets of neurons communicate, you get a restricted Boltzmann machine. We'll go over all that in the next two classes. Questions? Guys, any questions on streaming? Yes?
This is something you do by itself, or would you have to how would you, like, I'm just kind of confused, like, what are some of the applications?
This is literally content, the Hopfield network originally was just literally content-addressable memory, right? So you could store patterns, and you could start off with some random thing close to it, and it would remember things. So things like, denoising, whatever, right? You could also use it, for example, for pattern recognition, in the sense that if you stored 10 digits, and you got a corrupted image, which digit was it, right? But then if you go one step ahead, and if you begin think of adding extra stuff, you can begin thinking of it as a generative model, and that's what Boltzmann machines are used for, right? Primarily as generative models. You can use it for classification, prediction, what have you. The reason I put this off to the 3 lectures on this is that this is not the primary thrust of our course. But if you took, for example, 707, they actually spend a lot more time talking about restricted Boltzmann machines, and deep Boltzmann machines, and that entire hierarchy of models. All right, thank you.